So the last time we were talking about softmax regression, and so the idea was if I have a multi-class classification problem, I can model the probability of observing y equal y condition on x being equal to x as the softmax of this linear map, and then softmax is multivariate. So I'll take the y coordinate that would give me the probability of that class for that particular sequence or like feature x. And then the idea was to try now to fit this. So there was some suggestion using quadratic laws, and for using quadratic laws, you can do it by defining by redefining the labels using the one-hot encoding, and then comparing directly to the softmax output, which is giving you the soft probability. So this is like hard label, this is the soft label, and you compare, and then you have a nice least squares problem. The second approach that we looked at was to look at the MLE, and so you look at the negative log likelihood, and you try to minimize that. The negative log likelihood would have this empirical risk minimization format. So it's like an empirical average of the negative log likelihood, and then you minimize it. And so we get this loss function, which is, some people call this negative log softmax of this z, evaluated y, the cross entropy. And this is like the composition with the other thing that, like in PyTorch, that people call this negative log likelihood loss, which is just negative log of p of y. So if you give me a label y and a probability vector, I look at the probability of observing that label and the negative log of that. So that's a very simple loss, and you can see that this cross entropy is just the composition of the negative log likelihood and the softmax operation. So the naming is not that good, but let's say we're stuck with this because people like who wrote these functions chose these names. So the main thing to notice is that this z here is like real valued, a real valued vector. This p here is like a probability vector. So usually easier to work with these like inputs to the softmax, which are like free. So these are sometimes called logits. It's a multivariate version of the logit. So logits go in, and then the labels, and then you get the result. So with this notation, the cross entropy notation, you can write the ERM problem like this, which is very suggestive of usual linear regression, or it's like multi-response regression, where the quadratic loss is replaced with just this cross entropy loss. So the procedure is very similar, it's just the loss is now a bit more complicated. Okay, so questions, that was the setting. And yeah, last time I went over how this all looks in PyTorch, and I want to go over this in more details. How visible, let's see. Yeah, so again, questions. So I just want you to like get comfortable a little bit with this sort of the way that people do things in Python and also like PyTorch specifically. So this was trying to like give you some intuition of what the softmax is doing. So you can import this torch.nn has like a functional, say, module, and we're importing it as f. So f dot softmax is like defined there, so you can now apply softmax on the different dimensions of a tensor, and then we define a linear map. So a linear map is defined. So you do this. This torch nn contains all these interesting they call it layers or modules. So you can think of them as functions, basically. So different functions that people implemented. There's an input and there's an output. Usually the input is like features. The output could be anything, but in the end, hopefully it's like something about the class, like class probability or something like that. And one of these, and then you do import torch.nn as nn, and then I can do an nn.linear, for example. So this linear is capitalized, so it's a class. So I'm instantiating an object from this class, and you pass two parameters here. So if you do this, you can see there's in features and then out features and like a Boolean parameter bias, whether you want to bias or not. So in features 2, out features 3. The default for the Boolean is true. So I'm just going to leave it at that. So bias here is what? It's like a statistical bias or machine learning bias. It's just the intercept, right? So what this is implementing is, let's say W or theta times X. Theta is a matrix times X plus B, which is a vector. So that's the bias. So if I do the like print it, it just gives me an idea of what this is. It's like a linear map or a linear layer. 2 features in, 3 features out. Bias is true. So what really it's doing inside or like behind the scenes is that it has a weight, which I can access using. So this lin is now as an object, right? So from this class, so it has a lot of properties that it inherits from. That one of the properties is the weight. So that weight is a matrix. So you can see here, and you can see the class is of type parameters. So it's a let's see if this works. Probably not class. What should we type? Type. So you can see the type is torch nn.parameter dot parameter. So that's the type of it. And it's a parameter. So for example, you can optimize over and such. And you can see it's like requires grad is true by default because it's a parameter. So whenever you build more complicated functions out of it, then PyTorch keep tracks of the gradient of those functions relative to this if you want to ever compute the gradient. And then it's 3 by 2. So why it's 3 by 2? Because the input feature space dimension is 2, output is 3. So you multiply by a 3 by 2 matrix. So the features are 2-dimensional. This translates from 2 dimensions to 3 dimensions, right? So if you multiply this by this matrix 3 by 2 by a 2 by 1 vector, you get a 3 by 1 vector. So that's what you expect. And if I do data, this takes the data out. Now you can see it's a tensor. It's no longer a parameter. It has the same information, but I can, for example, now because it's a tensor, I can set the data of it. The data of it is really just the value of it. I can set it to whatever I want. Right now, because I created it this way, like it's randomly initialized. So the weights are randomly picked according to some distribution. If I want to like set a particular value for it, I can do. So that's that. And here, there's also a bias parameter. It's also a parameter, and then data, this accesses data. You can see when I do this, the first one is just the weight that we saw. The second one is a 3-dimensional vector. Okay, so you have a sort of 3 by 2 and 3 by 1. So the first one is 3 by 2 gets multiplied by the x, and then the second one is a 3 by 1 vector. So far, so good. And then here I'm just setting them to like specific values. You can see I set the lin.weight.data to this torch tensor, which is like 3 by 2. So this is how you define a matrix 3 by 2. So it's a list of rows. So each row is a list. So it's a list of lists. That's how you define a matrix. And it's really a list of rows, each of which is a list. So that's 3 by 2. And then the bias is just like a list, which is a vector. So you turn it into a torch tensor, and then that's what you get. And this is really calculating like W times X plus B. And then we did this calculation. So if I have a torch tensor, which is, this is 1 by 2 because it has one row. And if apply the lean, so this is how you apply these maps. So lean on X, this gives you a three-dimensional vector. We did this calculation. And if you have a tensor that you input to this, so the tensor here is now 4 by 2. As I mentioned last time, these things are designed to operate on the rows. So this dimension is the batch dimension. So each one, you can think of it as an observation. So it's one feature vector for one observation, and your model just operates on them separately. So you apply the linear map to the first row, you get a three-dimensional vector, so put it in the first row of the output. And you apply the map to second row, and you put it on the second row here. So if I want to, for example, access the second row, this is how you can access the second row of the matrix. Okay, so we can access the second row here. And if I apply the lin on it, we should get the second row here. Okay, so we get this. Okay, so it operates row by row. So if I apply it to the second row here, the third row here, you get the third row here. Okay. And then the operation, what it's really doing is, we went over this again, X multiplied by the transpose of the weights on this side plus the bias. So that produces exactly this. So I'll let you figure this out for yourself. So that's a linear map or a linear layer. Really, like mathematically, it should be called affine, but it's called linear for the same reasons as all other namings that are not necessarily ideal. So it's an affine map defined because of this bias. But you can also think of it as a linear map if you think of the bias as just a feature. So we're not going to go into like too much, like we're not going to be pedantic, the linear and affine are sort of the same. That's the basic model, linear models, right? And if I want to do softmax regression, I can think of it as a more complicated model. So it's so the NN linear that we had, right? This guy is actually is defined like that. So class NN linear inherits from NN module. So they defined it like that. So here we're going to do our own class. So class is a class. So softmax regression, that's the name that I'm giving it. It's a subclass of NN module. So it inherits everything from this. It has a lot of properties, so it inherits those. Then this has a constructor, or like in its function. So it takes self, all these like methods take self, which is an instance of the object whenever we create it as the first input by default. You can call it whatever you want, but the convention is to call the first argument self because it points to itself, like the object that's under consideration. You pass it input dimension. The rest is like whatever I want to do. Input dimension, output dimension. Here I'm calling the constructor of the class that's above it. It's like the parent. So it initializes whatever NN module and it does for initialization. This is like, again, default. Usually you do this. And then here I'm defining my own thing. So here I'm having a property. I'm calling it linear. I could call it whatever I want. Self.linear is my linear layer. So NN linear, input dimensions, output dimensions. So it creates one of these linear maps, really affine maps. And then I define this forward method. So this is all these NN module classes, like objects that you drive or classes that you drive, they have this forward function. And what it does is that it gets called whenever you apply this to some data. So whenever, for example, we applied, let's say lin, here, it would call the function forward of this object. So this has a forward function. So you can see this has a forward function, like, and it's really, we're calling that. So this like operation is just the shorthand for, so I can do this, which is really like a convenient way of, instead of saying like forward this. Okay, so when I do this, I'm calling forward. The first argument would be lin, that's the self. So it's really like going to call the forward function, lin and x2, okay, of that class. And so I have access to all the like properties of this object that I want. For example, I have access to the self is going to be that object, so it's going to be the, I have access to the linear property that I define, which is the linear layer. So this is going to contain the parameters that I'm trying to optimize. So this has some parameters like weights and the bias, and this is contained in this. So I'm going to apply that with whatever current parameters that it has to the input x, and then I apply the softmax on the first dimension. So the like the rows is the 0th dimension, the first is the column. So I'm applying it across columns. So that's what we want to do. We want to apply it on each one of these because each one is like a data point. So we apply the linear map on each row, and then we apply the softmax on each row. That's exactly what the softmax regression is supposed to do. So that's exactly that model. Very simple model. And so that defines our class. Okay, questions? People know this stuff, or maybe a review for some people, like new for some. So I have the class. You can now put it in some other like nice sort of Python function or the file, and then call like import it and then use it. So here I'm going to use it. So set the seed to something which allows us to have like reproducibility. I'm generating an object which I'm calling true model. Softmax 2 and 4. So the input dimension is 2. The output dimension is 4. Sorry, input dimension 2, output dimension 4. And then I'm printing the model. So let me print the model. Print. So you see it's just softmax, and it has a linear. This is the name of the property that we define as like this linear layer. So this I could call whatever I want, but this is the class of it. So it's an object of class linear, input features 2, output features 4, bias is true. And if I do each one of these models, so because it's like inheriting from this, it has a parameter method. So I can call this parameter method. So you can see, for example, I do print true model dot parameters. This is a method, bound method, and then the way you have to call it is like this. So what this does is that gives you, like in an ideal world, gives you like a list of the parameters of the model. Well, you see what it gives you is really a generator, which is a fancy way of returning a list. Instead of returning a list, it gives you something that you can iterate over and get elements. So for example, I could do for, this is how people usually do it, for like a parameter in this, then print parameter. Okay, that would give me iterates through these parameters, and it gives me, there are two parameters. One is a tensor, the other is the bias. So that's exactly the parameters of the linear guy that we put there. Another way, like this is how you do it. Usually, like reasonable way of doing things. Or I can just, if I'm not like lazy, I can just apply lists to it. It turns this generator into a list, and it's return the list. Okay, so that's a fast way of doing it. Not advisable for like a big list like that we had. That just one comment that the advantage of doing this is that if I define something else here, right? For example, use like unused linear layer. So I define another, for example, layer with this like 10 dimensions here. Now, if I create something like that, you'd see that now like the parameters of the second linear layer is also listed here. So whatever I define here automatically get registered. So the parameters of it gets registered among the parameters of my class. So this is a nice feature of this NN module that you can like put like anything that you want here, and the parameters of it is like among the parameters of the model. So it just collects everything together. And if I do, for example, print the model itself, you can get more information. So you see this has some sort of understanding that this now has two components, both of them are linear. Okay, so that's how you can make more complicated models. But for now, that's just that. So this creates a softmax regression with random weights. Okay, and then I'm calling the true model because I'm going to assume that this is really the model that's generating the data. So I want to generate some data from the actual softmax model and then see if I can like recover the parameters. So far, so good. Questions? Stop here, maybe see. If you haven't like worked with Python or like PyTorch, this might seem a little bit like overkill, but it's a nice way of doing. We don't have to do this. You don't have to define a class. We could have done this easier, but this is a nice way to encapsulate the model into a class, and then you can just pass it around. Like there are a lot of functions that work on these objects, as we'll see. Sounds good? Yeah.
Confused in the class that you define. What is weight and bias?
So this class creates an object that has a property linear, which itself is an object from this class linear, right? And any object from this class linear has a weight and a bias, right?
We define this bias and weight, or
okay, so whenever I create this, because so this uses a default constructor. So whenever I didn't pass it anything, so what by default is going to generate like a random weight, right? That's what happens. So if I, for example, rerun this, you can see if I print the parameters, I created the model, right? If I run it again, I get the same thing. The reason why I get the same thing is because I set the seed to be something fixed so they can reproduce. But if I just comment that out, every time I run this, I should get a different set of weights. You see, changes. So I get a different set of weights just randomly picked according to some distribution. That's a good point. I can just redefine it to be what I want by doing this procedure. So I can say do this. True model dot linear is going to access that linear property, and then dot weight accesses that parameter weight, and then dot data accesses data, and I can just put whatever I want here. And then the bias the same way. So if I do that, and then let's say print it here, after doing this, so originally it's initialized to that, and then if I do this, so originally it is that, and after I print the parameters, it's what I define. Okay, so I can like manually like go and set it equal to whatever I want. Sounds good. Let me comment this out. Any other questions? Okay, so we have that. Now I'm going to generate a sample of size 2000 and train the training sample size. So again, softmax model is not a generative model. So it just gives you the probability of y given x. So if I want to generate data, I have to like supply the marginal distribution of x. And here I'm just for simplicity doing Gaussian. So this creates a Gaussian matrix, standard entries like normal 0, 1, 2000 by 2. Okay, so this would be 2000 or say n train by 2. Okay, and then I'm going to apply the true model, right? So true model to X. So true model is the softmax regression. So what does this line do? What do you guys think this is doing? If you understood what we did so far. Increase the size a little more. Too big. So what is this doing? Is this visible from back there? Okay. Anyone? I should clear this so that you don't see. So what would I get for this probability? Like I'm calling it probability because it would be like has the meaning of probability. So what is the size of it, and what is it like? How is it computed? So the true model is an instance of this softmax regression, right? So you should think of really these as like functions with a lot of bells and whistles. So when I apply this true model to a vector, it's going to go call this forward function, and it's just going to apply this to every row of my data. Okay, so it applies the softmax and then that linear map. Right, so it's really applying the softmax regression to my input data. And it's going to do it on each row. So basically for each row, we get a probability vector. So what is going to be the size of that probability vector? So that would be 4. So the 4 that I'm putting here is just the number of classes. So the input features are two-dimensional. So we have like, let's say the breast cancer data. Assume that we have 4 classes. So this is going to output a 4-dimensional probability vector. So if I do this, you get the size 2000 by 4, and you can look at each row of this. If you're good at like doing this calculation in your head, the rows have to sum to 1, right? So they're probably, so if I want to like verify this, I can see if this works. Sum the rows, oh, they probably, okay, works. You can see they're all ones, okay? So this creates some sort of a the probability of basically y I belonging to each class. So this is like the probability of y1 belonging to each one of the classes given x1. There's the probability of y2 belonging to each one of the classes given x2, and so on. So now if I want to generate the labels, what should I do? I want to generate like the see if we can get this. So what this is really doing is creating this. So this is really producing this vector, S theta X. Theta contains both the bias and the weights. So how can I generate the labels now? Anyone? How should we generate the labels? If I want to like generate labels from the softmax model, it's like softmax regression. There are 2 sets of labels that they can, like, there are 2 ways that they can generate label. See if you guys can So I'm giving you, like, for this row, I'm giving you probability of belonging to classes. What is a natural way to generate the labels now? To have like the softmax being the model that's giving me the conditional probability of y given x. I want to generate from that model. So I generated from x, and then x, like, pass through this model, give me the probabilities. Now I want to generate the labels. How do you generate labels?
Which ones that have one of the largest probability in each row, or is that state should be two?
The label should be 2. So this is label 0, 1.
No, 4.
Label 4. Okay, so what you're saying is that take them the argmax, so the argument that maximizes, right? So this is going to give me like a specific row, like label for each row, right? So I can do that. So this is just sample from multinomial distribution. So this knows more than us. So take the argmax of each row, which reads the mind. So this was wrong. Okay, very nice. So we got it to make it an error. Take the argmax of each row of okay, so we found a mistake. Well, not mistake. So this is like this is the corner case where like the Copilot is making an error. So what I want to do is like take the argmax. I've done it below, but that give me a deterministic set of labels. So that's not how you generate from this model. That gives you something else, which is also very useful. But every time I do it, there's just one time to do it. But I want the probability, like I want a probability. So this is a probabilistic model, right? So even if I fix x, there's randomness in y. So it's not going to be always like determined. Even if I give you this probability vector exactly, and when you generate from this, you have to sample from this model. So what you need to do if you want to sample from the model, you have to sample from each one of these rows as a probability vector. So it's going to be a multinomial, like with a one observation, or they call it categorical distribution. So for each one of these, you have a categorical distribution. You just flip a 4-way coin with these probabilities. If it was just 2, it's just like flip a coin. But this is called a categorical distribution. So I have to sample from this categorical distribution. Every time I do it, I get a different thing. I'm going to get this label most likely, more likely, but I could equally get this or this or this thing. So if I want to sample from this, I'm going to do this. And this is going to give me like, from a categorical with these probabilities, sample gives me these labels. There's another way of doing it, which is do a multinomial with one observations. Now the argmax is something else. So this is, I can also compute the argmax of these probabilities across dimension 1. Dimension 1 is the columns. So in each row, I'm going to go take the argmax across the columns. So this is going to give me another something else, which is why let me do this here. So why I'm calling this the base. So this the base classifier would be this. So why I'm calling this base. So this is going to be that. This is always going to be the same given the probabilities. Sort of. Why is it the base classifier? Because we showed sort of that if the model is true, the optimal thing to do is to take the label of the maximum. Like remember there was this like chapter 1, argmax of this over y is the optimal rule. So if I give you the exact this probability distribution, if I give you like the oracle gives you the probability of joint distribution x and y, you compute the conditional probability of y given x, and then your rule for that x would be optimal rule would be the one that maximizes the probability conditional probability of y given x. So in the binary case, it would reduce to like computing the regression function comparing with 1/2. But in general, the rule is argmax over y. So finding the argmax, the maximum, like the label of the maximum associated with the maximum probability is really giving you the Bayes rule here. Okay, so these are the labels that the Bayes rule would predict or like would have the optimal rule. And whenever you sample, sometimes you match this, sometimes you don't. And the difference on average is going to be like the limit of the problem. Okay, how well the problem, like the best that you could do for this problem. The difference is clear. So if you sample, you're generating from this model. But for this particular set of features, this probability is fixed. For this particular set of features, the optimal like label would be this. It's very similar to the logistic regression. There is an optimal label given the feature that may or may not match the true the label that you actually had for that data point. And the difference on average, like if you average over all samples, is what constitutes the Bayes error. The difference. So that's what I want to like hopefully get across through these simulations. So if I now plot this, so I'm now going to plot. So this function is going to go and pick the unique elements in Y. So this gives you all the classes, and then I iterate for every class in these classes. I'm going to go look at the indices of the points that match, like the labels that match that class, and then plot those points with, this is going to, because I do it separately, this is going to plot them with different colors. So I'm going to do this first for this Y class, which is the optimal label, and then I'm going to do it with the actual label that we sampled from. So let's do this and see what happens. Okay, so that's what you get. So these are the colored, the same points colored by the Bayes label, and these are the samples, the actual thing that you get. So you can see for the Bayes, you can all see the decision boundaries basically. So decision boundaries are sort of determined by like the intersection of these hyperplanes or lines, and this is something that you're going to like work out in your homework problem. Why decision boundaries look like this? It's a little bit more complicated than binary classification. In binary classification, it would be just a line. To one side would be one label, to the other side would be the other. But here, because we are like taking the argmax, so in this region, all the points here have like argmax matching one of the labels in class 3. And in this region, it's going to be class 1. And why it looks like this, hopefully, if you work with the mathematical formula, it becomes clear why it's just in general going to be like each one of these regions would be the intersection of a bunch of hyperplanes, and these hyperplanes, but the points that are on these hyperplanes are the decision boundaries. So there are multiple decision boundaries, but these are disjoint sort of up to that like ambiguity at the boundary. This is like a horrible mess. So this is showing that this problem is like very noisy. Okay. So before doing this, is there, so you can see like, so I'm unlikely that I like get a good result. I'm going to get something, but not necessarily that well. Can I like improve the signal to noise ratio here? How can I like get something which is closer to the Bayes rule? How can like the Bayes risk here, like the Bayes minimum error, go down? What should I, if I want to generate from a model that has more signal, it's not as noisy? What do you guys think you can do? Think about that. I'm going to come back to that. Okay, so maybe think about how we can generate. So what should I change to get a better picture here? Okay, but before doing that, while you think about this in the background, so let's try to fit the model. Now I have a true model that's generating the data. Now I want to like fit it or like estimate the parameters. What I can do I can still use my own class, that's the good thing about writing a class, is that now I can reuse it. So I'm going to call this class again with these parameters because there are two features. You can see that two features, two-dimensional here. X was like n by 2. And I have 4 classes, so n 2 by 4. And this creates a model, and it will have exactly the same like the structure as the softmax regression that generated the data. It's just that the weights are randomly initialized. And then I can do gradient descent on the weights of the model given a loss that's determined by the training data, and that the parameters of this model is gonna like improve and hopefully get close to true parameter. Okay, but this model is my like training model. Okay, so I had a true model, the parameters are fixed, generating the data. Now I have a candidate model initialized randomly. So if you like look at the parameters, because we're not specifying specific parameters, they're going to be random. This is what I wanted to maybe like add. We could write our own, like we had our own gradient descent. But here I'm going to use PyTorch sort of packaged SGD. SGD stands for stochastic gradient descent. I'm going to talk about that, but for all intents and purposes, it's just gradient descent. Okay, gradient descent with a bit of bells and whistles. So what you can do that helps you like not worry too much about writing your own version is like I can pass this torch optim.std the parameters of the model. Remember, this is like model the parameters. This is going to be our model. In our case, it has 2 parameters. It has a linear layer only, and that has like a weight and a bias. So this contains basically the list of those parameters. I pass it to this optimization object, and it now knows about those parameters. It has pointers to those parameters, so it can now manipulate those parameters. And there's this learning rate, the momentum. You know what momentum is. So learning rate is 0.2. Momentum, as I said, is equal to 0. How am I going to use this optimizer? So what it does is essentially has one useful method, which is a step. So I take a step. So if I call optim.step, it takes in a step according to the gradient of the parameters of the model. It does nothing except taking a step according to the prescription of what gradient descent is. But what I have to do, we'll see. It knows the parameters. So whenever I call a step, it's going to go look at the gradient of those parameters, like the gradient property, and then takes the step according to the gradient. So adds the gradient multiplied by this learning rate to those parameters, and that would be the step. So the gradient has to be computed elsewhere, and the way that you compute the gradient is you do it however you want. So whenever you call this optimal step, you have to have the gradients in place, and we know how to calculate the gradients. Okay, so what we want to calculate the gradients with respect to some loss. So I'm going to define my loss here, and I can come back what the loss is, but well, maybe let me talk about the loss first. Okay, let me talk about the so let's say I'm going to come back to the loss. So this loss gives me a loss. So I give you the model. So it takes the model. Maybe let's work through this to be clear. So the model, I take the model, and I apply the model to X. So X is my training data up there. So X here is, remember this is the data, and then Y is the training data. So this is like a 2000 by 2 vector, and then Y is also 2000 vector. So these are the labels, right? Remember the Y's are the class labels. So so this takes the X is a global variable, so it's there. So I apply the model to this. So that model is my current softmax model as the current parameter. Applies it to X to each row. So I get these probabilities. What I'm doing here is calculating the this guy. Because I put the softmax in the model, I'm not going to use this cross entropy idea. I'm going to use this because the softmax is part of the model. What I really need to do is this probability already contains the softmax. So I'm just going to apply this negative log of P of Y. So what this is going to do is this is really P of this is like P of I, like probability I and yi. So that's really it. So this is like for each I, for each row goes and evaluates that probability at value, which is the observed y. So it's like P sub y that I wrote. So it's our model predicts this probability, and I'm going to look at the actual element of the probability that the label is corresponding to. So if my label, so if I'm predicting, let's say class 3 is very high, and my actual label, training label, is like at the third location, then this is going to be very high, and because later I have a negative, the loss is going to be low. On the other hand, if that row like is predicting label 2 very like highly, but the actual label is label 3, I'm going to get a very small number at this location, and so the negative row is going to be large, okay, small. So, but basically, if you understand what this is like negative log P. It's just P of xi. So it's like we had it somewhere here. So this is like probability. That's basically this. Okay. So this gives me that probability vector. I'm choosing the right I coordinate. So that's really the log likelihood, and the negative of it is. So this is the log likelihood, and the negative would be negative log likelihood, and then I take the average. So this creates that negative log likelihood. The way that this is like arranged is like this is range of n train is just going to be like 0 up to n train minus 1, and then the y's are here. So each row is going to pick y, like I, yi. That's what it does. So I'll let you think a little bit about this, but this is exactly calculating the log likelihood. And this is the negative, and then I take the average. So this is going to be my loss. So how does the model come in? The training comes in as x and y. This is fixed. The model like it passes, and every time I change the parameters, I get a different model. I get a different loss. So I can measure how well I'm doing in this negative log likelihood. So you could have done cross entropy if your model was really linear. If the softmax was not there, you could like leave the softmax out and put the softmax into the loss. It would be the same. So that's what we discussed. So far, so good. So that's the loss. I'll let you like contemplate it later for yourself. But if I have the loss and I have that optimizer, like this like establishes the link between the parameters of the model and the optimizer. So what happens now is that I have the model, I apply this my loss function, I get the loss, and I'm predicting the loss, and then yeah, so I'm predicting for every, so this is going over the parameters of the model. So name parameter is another method. So this produces both a name and the parameter, and I'm printing the name of the parameter and the parameter that graph. So this prints the gradient of the parameters. At the start, there's no gradient, so these are all none. So I'm hoping to get none. And then I apply the loss backward. So loss.backward, if you remember, this is just calculating the gradients. So it calculates the gradient of this loss with respect to whatever parameter went into constructing that loss that requires gradient. So this loss is constructed, you can see this loss is constructed via this model, and this model has parameters that require gradient. The rest, so if you look at x, for example, this is also a tensor, but require grad is false. Y is also a tensor. So this requires grad is false. So these are tensors, but they don't require grad, so these are not like considered. The only thing that's considered are these parameters that are inside this model. Requires grad is true. If you remember, the parameters are by default. That requires grad is true for them. And so what this does is that calculate the gradient of the loss with respect to those parameters. And so populates the gradient field of those parameters. So now when I go through the parameters of the model and print the gradient, I should get the gradient of the loss with respect to those parameters. So if I run this, you'll see from the first, there's none here. So these are the gradient, the gradient of linear.weight. So that's the name of the parameter. And linear.bias, there's nothing. And then once I do this loss backward, it just populates the gradient here. And this is the gradient of the loss, the log likelihood loss that we have with respect to the weights matrix and with respect to the bias. Now that I have gradients, I can do gradient descent. I have the current parameters, which are the parameters of the model, and I take a step in the direction of the okay. The way I do it, so is this clear, sort of? Okay. There's a lot of indirection. So implicitly, when I pass the model, this loss gets constructed out of that model, and that model has parameters. So all those parameters went into constructing that loss. So the PyTorch keeps track of everything. So this loss, like the gradient of there's a gradient function that points to those parameters. So when I call this backward on the loss, so it goes and populates the gradient of whatever was there in the construction that required the gradient. Questions? Maybe contemplate this a little bit. So there's no optimization here. It's just we can calculate the gradient of the loss with respect to the parameters of the model. Okay. And if it feels good, then I'm going to do my own gradient. So because I have gradients, let's say, if I look at the model, that linear, that weight, that's the weight parameter. Now that I have the gradient in this parameter, so that's one of the parameters. Dot grad would be its gradient, the gradient of the loss with respect to this parameter. So if I take a step of size like 0.2 in the negative direction of the gradient, this is the gradient descent step. And if I do it for the bias, it's going to be the same. So this operation is going to be exactly the same as if I apply this optime.step. So if I apply this optime.step, what it does is it goes and just does this and updates these weights. So this linear.weight is going to be equal to itself minus 0.2 times that. So that's the prescription for gradient descent, because we set it up with layering rate 0.2, right? So we set this up with layering 0.2, momentum is 0, all the other default parameters. It's going to go take a step of 0.2 in the negative direction of the gradient, whatever gradient is there. So if you check this, so if you run this, the first two lines are printing my own gradient. This is the gradient step. So this is the updated parameter model. So that's the parameter, the weight update. This is the bias update. The second line is after I do this, I'm looking at the parameters of the model and they should match. So you can see that this matches exactly this, right? So this matches exactly that. Okay, so this is just a fancy, simple way of doing gradient descent without needing to write this. I'm just doing this. Behind the hood is just gonna update all the parameters by taking it direction, like a step in the direction of the gradient. So this doesn't compute the gradient, doesn't do any optimization. It just takes one step. So you just have to have the gradient in place. Does that make sense? Let's look at this a little bit. Questions? So if you understand this, which hopefully you would, once you go through it. I think we lost. Right. So this is going to be the gradient descent in PyTorch in just a few lines. Sorry, I'm pressing the wrong button here. I just wanted to. Okay. So again, I'm doing initializing the model. This is going to initialize the model. initialize the optimizer passing these parameters. Number of step 1,000, momentum, let's set it equal to 0. And then for each iteration in range of the number of steps, I'm going to calculate the loss of the model. Okay, so this establishes the connection between the loss and the parameters of the model. This loss backward calculates the gradient of the loss with respect to those parameters, populates the gradient of those parameters in the model. This optimization step, because it knows about the parameters of the model, just updates those parameters by taking a step in the direction of gradient. This zero grad, now I can like call this another feature, opting that zero grad. This just zeroes out the gradient of all the parameters. And this zeroes out the gradient. We had to do it like by hand. But because this knows about the parameters, zeroes out the gradient, because otherwise the gradient accumulates. Just next time, when you calculate this, when you do this, it just adds it to the gradient that's there, which we don't want to. And then I'm just like keeping track of the loss. So this is a list that's gonna like keep track of the loss, and then I can plot the loss, and you can see it like nicely goes down. It's actually very smooth. And just flattens out, so like after a few steps. So gradient descent on softmax regression, and sort of you're done, sort of. Is there any questions? So if you understand this, basically it's essentially the same as the gradient descent that we did. I'm just calling out all these things. This one we didn't do. We didn't calculate the gradient ourselves, so that's why we're using PyTorch. Otherwise, there's no point in doing it. But this is useful because it does that step, and then I can replace this with like more fancier optimizers. They take like the step in a more like fancier fashion, but they all rely on the gradient. So you have to have the gradient, and then this step just zeroes out the gradient, so that in the next iteration we calculate the correct gradient. Okay, gradient descent in PyTorch in a few lines, and so now I have this. So what this does is that the parameters of the model in each step gets updated. So start from some parameters, and then I can print the true model linear weights, let's say with the model that we trained, and you can see there's some matches, sort of matches. There's some mismatches, which I'll let you figure out. That's pretty okay. I mean, there is some ambiguity, as I mentioned, in the softmax parameter. So parameters are not identifiable. So it's hard to judge by the precision of the parameters, but let's say in this course we carry out prediction. How can I like verify that I'm doing good? So the loss is going down, but is there a way I can like verify that I'm actually doing good? How should we? This is like the training loss, and the training loss is related to the maximum likelihood or the likelihood loss, which is not necessarily generally what we care about. It's a valid loss, actually. You can measure it, but what this is measuring is the training negative log likelihood loss. Is there a way that I can verify that I'm actually doing good? Even for the training. So I don't have a test. I can split into training and test, right? But because we actually have the true model, I can generate more data that I haven't seen from the true model and then test on those. But the loss that I care about is not usually the log likelihood, which is fine. By the way, let's say I want the 0-1 loss. Okay, so what I can do is I can try to calculate so this is the final model. Now the model, when you access it after this point, has the right parameters. These are the parameters that we learned. I apply it to training data, and then I calculate the argmax. So this is the hard labels that I want. Right now, Y class would be the predicted labels. So if I want to predict, this is like the plug-in Bayes rule, because we now estimated the parameters. This is the optimal set of labels if the model is actually true. And then I calculate like the accuracy, basically, the opposite of its classification. In what fraction of the cases the true label matches the y-class. This is still training, but the loss is closer to what we care about, which is 0-1 loss, like the opposite of 0-1 loss. And then I'm calculating the Bayes accuracy, which is like applying true model to the Bayes labels and then compare it with the y. So this is the sort of the best possible. The top is what we got, and you can see we're very close, and actually like we're beating the Bayes risk. So we're actually like breaking sort of something here in mathematics. Which are very close. So the reason this is not the actual Bayes, because it's also like based on the 2000 sample. The Bayes risk would be based on infinite samples at the population level. So we need to calculate the. So you can calculate it probably by hand. What the Bayes area. But comparing these two, you can see here you don't really need the test sets because you have sort of the true labels. So you have the true, this is the true part, the probabilities of the true from the true model. And this gives you the true Bayes labels. And so you can see the accuracy is very close. The accuracy is not good, okay? But it's like 0.39 accuracy, good or bad. In this case, it's as good as you can get. So you can't improve beyond this, right? So how to know if you're doing good or not? That's if you know the true model, that's how you know. Okay, it's not possible to improve beyond like about 0.39. Right, so you can increase if you want to get the actual Bayes error, so you can do it like a 10,000 sample or so from the model. And this improves. This should always be like the population level better than this. So very close. So that's good. Questions? So we didn't need to do tests chain to verify this because we have access to the true model and I can calculate the actual Bayes, the limit of the problem, so I don't need to worry about. But you can actually calculate on a test set and you can convince yourself that it's going to be the same. Questions? So this is saying that the model is really noisy because the maximum that I can, like the maximum accuracy I can get is about 40%. So now let's go back to the original problem, like the question that I asked, how can I make the problem less noisy? I want a true model which is less noisy. So what did we do in the logistic regression to make it less noisy, if you remember? There was the SNR type of like variable. So I can do something here. So this parameter is chosen randomly, right? So I can do something to this parameter to make sure the classes are more defined. Softmax sort of, I mentioned, it's like gets saturated when the argument becomes big. It's like the sigmoid function. So if I make the parameter theta bigger, in absolute value bigger, then it would forces the classes to. So you can think about this or recall what we did, but here I'm generating the true model. What I'm going to do is I'm going to uncomment this. Right, so this goes over all the parameters of the model and multiply each one of the parameters by 10. Okay, so just the size gets bigger. So it used to be like initialized like this. Now I'm multiplying everything by 10, so everything becomes bigger in size. Now I'm going to generate data. These are the labels. So you can see these are this is the sample version, and you can like see like the contours of the classes. So this is less noisy. So if I like do this business, the problem becomes easier. So classification problem becomes less noisy. I'd expect the base error to go down because the base error is the difference of the labels that I get. For these things that are here, like most of the time I get the correct label. Only the things that are near the boundary are going to be like problematic. So the base accuracy, you'd expect this to go up. Okay, so this is the true model, less noisy. I'm going to run this. So these are just this, and then this is really too good. I don't know why it's too good. Yeah, okay, fine. Just parameters you can see are not that great. Two parameters, like this is the final parameters. They're okay, but then I can just compare the accuracy. You can see the base accuracy is 0.84. It went up 84%, which you expect because the problem is like that's the limits. We can't improve beyond this. But then we also see that our model is close, like 0.85%, which is good. And then you can also see some interesting thing that the parameters are off. So you're doing okay. Okay. This is very off. And I'll let you think about this. Okay. Although the parameters are not like the same, but you're predicting correctly. So this is one point, just one, like bear with me, like we have a few more minutes. I just want to tell you what SGD is. So that's also one of your homework problems. So what is why this is called SGD? Is really doing gradient descent, as we've seen. So what is SGD? Stochastic gradient descent. And why it's called a stochastic gradient descent. Anyone knows that? How many have heard SGD? About SGD? Not anyone, okay. So it's very like sort of natural when you do empirical risk minimization. If you really remember what we did with empirical risk minimization, we replaced some population loss expectation with empirical average. So we really wanted to minimize the expectation, but we didn't have access to the expectation because we don't have the actual distribution. We replaced it with the empirical average based on the training data. So this is already a stochastic version of the actual loss, the risk, not the loss, but the risk. So in SGD, what happens is that instead of using all your training data, you just use like a subsample. You get an even rougher estimate. So if instead of using all the 2000 samples, I use like 100 samples from my training data. It's still the approximation of the true risk, but it's a noisier approximation. But it's easier because like 2000 might be too cumbersome to calculate, but 100 might be easier. So I have to evaluate it. If the model is too complicated, there's a cost of calculating this loss. There's a cost of like summing all those. So each time I'm going to run it on a subsample size 100. That's usually called a mini batch. SGD is just the extreme case where you just use one sample every time. Okay, stochastic gradient descent. Traditionally, you just approximate the loss by just one sample. It's a bad approximation, but it's faster. People nowadays don't do it. And if you do it, in this case, it's not going to work that well. But I can do, for example, let me show you how we can do this. Written like I can have to redefine the loss here. So I'm just redefining my loss here, like rough loss. So this takes a batch size, size 100. Each time I want to calculate the loss, I'm gonna pick a set of indices from 0 to the number of samples of batch size, and then I'm just subsampling. I'm taking the rows that are indexed by this index and the rows like the labels here. So this is like gonna take 100 rows in the data features and the labels. And then I'm gonna this is X sample and this is YS. And I'm just gonna calculate the loss based on, so the probability, the rest is just exactly the same thing, but that's based on this subsample of the data. So I calculate the loss based on the subsample and you can see what happens. So let's see, it's the same thing. I'm actually using a momentum here. You can see like there's a lot of like noise here, right? So this gets noisier. Okay, actually, I think. Yeah, so let's do like batch size here is like, let's say 100. So quite noisy. Let's say if I do 10, you get a very, very noisy situation. If I do 100, you get a better thing, but still noisy. If I do like 500, so things converge, but there is some noise. But in practice, that's what people do. So instead of like passing your entire 1 million sample of images, let's say through a very complicated model, you do like 100 at a time. Something very interesting happens in this case if I just do 2000, because that's the maximum amount of data they have. If I just do this, you would expect that you'd get the same result as before, but you still get some noise here. The reason is what I'm doing here is I'm not doing sampling with replacement. I'm randomly sampling with replacement. So I don't get the original data back. I get like a copy of the data. Some of the data points might be repeated. This has some sort of bootstrap effect. But modulo that, that's what mini batch GD or SGD is. So that's what you do. It works still, and you pay like a lower price. The noise also sort of might be of interest separately. If you do with 2000, you're using the sample, the entire sample, but because we're doing something with replacement, there is some sort of uncertainty, like measure as well here, which is a different story, maybe for different time. One more point is that if you pass all your data, you can like, if you can redefine this to be better, so you can try to take your data and split it into batches so that you see all the batches. So the first 200, the second 200, and so on. And once you do a pass, this is doing it randomly. But if you do it like more principled way, after like 10 batches here, you see all the data. That's called an epoch, like the terminology. And then you can repeat again. Okay, repeat more. And this is slightly different than the gradient on a single loss, because every time the loss is changing, but because the loss is approximating the true loss, this turns out to work. Okay, so that's what people do in practice. And that's what I'm asking you to do for the MNIST data. I'm going to hopefully upload something so that you can like use that notebook to get the data, but it's a bunch of images. You just flatten it out and treat it as like usual, and then do softmax regression and see what happens. Okay. Good. Any questions? Okay. Thank you, guys. See you next time.